Hello everyone, this is lecture 17 of the subject analog circuits. In this class I am going to discuss RC oscillators, and there are two main types of RC oscillators. One is Vin Bridge oscillator and another one is phase shift oscillator. So, in the last class, in the lecture 16, I had discussed the basic principle of oscillator, how the oscillations are generated, what is the criteria for oscillations. Then I had discussed the classification of oscillators, right. So, in this class we are going to understand the Vin Bridge and phase shift oscillator, and ultimately the oscillator it generates a signal of a particular frequency. So, are very much interested in frequency. So, we will derive the expression for that also, what is the expression of frequency for Vin Bridge oscillator and phase shift oscillator, how we can vary the frequency. So, starting with the basics of oscillator. So, basically oscillations are produced by following the criteria that is called Bark-Hussein criteria. As per Bark-Hussein criteria, your loop gain it should be 1, that is mod A beta, and your phase angle, that is phase shift around the loop, it should be 0 degree or 360 degree. So, in any oscillator, in feedback type oscillator, I am not talking about non feedback, I am talking about the feedback type oscillator. Obviously, the feedback should be positive. There are two important networks, one is your amplifier and another one is your feedback network, that is your beta, fine. So, the total phase shift around the loop means this is your V naught, the output it goes to the input through this feedback network, and the output of this feedback network is let us say it is a Vf, and it is added to the input signal. So, the total phase shift around the loop it should be 0 degree or 360 degree, fine, we have to ensure that. So, it totally depends upon the type of amplifier which we are using, whether we are using inverting or non inverting amplifier. For example, if we are using inverting amplifier, the feedback network should give 180 degree phase shift, by which the total phase shift around the loop should be 360. If we are using non inverting, then obviously the feedback network should not give any phase shift. So, these things I had discussed in the last class in the principle of oscillations. Now, starting with the oscillator, that is the Vin Bridge oscillator, but before that one thing which I want to mention here is operational amplifier. Although we will study in detail this operational amplifier in unit 5, but why I am discussing it here at this moment, the reason is that in any oscillator we need amplifier. So, how we can design this amplifier? So, up to now we know that we can design this amplifier using BJT, that is BJT amplifier, or using MOSFET, that is MOSFET amplifier, and the third category is your operational amplifier, in short it is called op amp. So, we just know the basics of op amp at this moment, in detail you will study in further classes, right. So, this operational amplifier it is having two input terminals, one is your inverting input, another one is non inverting. This negative input is your inverting and the positive input is non inverting, and it is having single ended output. So, there is a op amp IC available in the market, that is your 741 IC, right. So, basically this operational amplifier is a difference amplifier which amplifies the difference between these two input signals. Now, this operational amplifier it can be used in two configuration, one is inverting and another one is non inverting. If we are applying the input signal at the inverting terminal, right, then your operational amplifier is called inverting amplifier, and obviously there will be feedback, in amplifier obviously negative feedback will be there, that is why output is connected to the inverting input terminal. This is your inverting amplifier. In inverting amplifier means it will give 180 degree phase shift, but if we apply the input signal at the non inverting terminal, then in this case again there is a negative feedback, and it is connected through a resistor here. So, the point is that if we are applying the input signal at the non-inverting terminal, then it is called non-inverting. Non-inverting means output will be in phase with input. So, remaining things just ignore at this moment, right. At this moment just we need to know that this is amplifier, op amp is an amplifier, and if we are using the inverting amplifier, then we will get 180 degree phase shift. If we are using the non-inverting amplifier, then output will be in phase with input. Although there are a lot of things that how we design this inverting amplifier, non-inverting amplifier, we add some registers, that I will discuss in last unit, in unit 5, right. So, these things should be clear. Now, starting with the first kind of RC oscillator, that is Vin Bridge Oscillator. Now, you can see that as an amplifier we have used this op amp, although we can use BJT amplifier and MOSFET amplifiers also, there is no issue in that, but this op amp is easily available 741 IC, it is very less costly, it is not costly in fact, right, we can easily buy it and we can easily use it, that is why we are using here it. So, you can design this Vin Bridge oscillator on the breadboard, just you require this 741 IC and few additional resistors and capacitors. Although, if you do not have this 741 IC, you can design like common emitter and common source amplifier that you have studied in unit 1 on the breadboard in your laboratory, right. So, in Vin Bridge oscillator, the first point is that in Vin Bridge oscillator we have used the non-inverting configuration of op amp. Non-inverting means this amplifier is not giving any phase shift. It means that we need to ensure that the feedback network should not give any phase shift, any further phase shift. By doing this, the total phase shift around the loop, it will be 0 degree or 360 degree, right. So, in the feedback network there are two branches, one is your R and C are connected in series, another one is R and C are connected in parallel, and it is connected to the positive input terminal, that is the non-inverting input terminal, right. This R2 and R1 register, it is just to set the amplifier gain, just by varying the value of R2 and R1 we can vary the gain of the amplifier. As I had discussed in the last class, we need this amplifier, it is required, right, because the principle of oscillation is that we are not going to apply any input signal and we are getting the output by amplifying that small noise voltage and by following the condition that is called Bar-Hussein criteria, right. So, now we need to calculate the frequency of oscillation for this Vin Bridge oscillator. For that, firstly we are going to calculate the loop gain, that is LS. LS is your A into beta, right. This A is basically gain of the amplifier. Since it is a non-inverting amplifier, so for non-inverting amplifier the gain is 1 plus R2 by R1. So, the point is that let us review it. Although you will study this non-inverting amplifier in last unit, just see to it. See, in non-inverting amplifier we apply the input signal at the non-inverting terminal, this is your output voltage V naught, and in the feedback there is a resistor R2. So, when we calculate the gain of this non-inverting amplifier, then we get 1 plus R2 by R1. So, you will do this derivation in last unit. So, at this moment just use this expression 1 plus R2 by R1, and obviously the gain is positive because it is a non-inverting amplifier, fine. So, this 1 plus R2 by R1, it is the gain of the amplifier, that is A, and your beta is Zp upon Zp plus Zs. What is Zp, what is Zs? Zs is, it is a series combination of R and C. What will be the value of Zs? Zs will be R plus, and the impedance of capacitor is 1 by Sc, right. And what is Zp? Zp is R parallel to 1 by Sc. Now, see, either you can use this expression R parallel to 1 by Sc by using Zp, or it is better to use Yp. Yp is 1 by Zp, right. So, whenever the capacitor is in parallel, So, it is better to use admittance in comparison with impedance, right. When we use admittance, then the calculation it will be simpler, right. So, y p is just the combination of y 1 plus y 2 here, right, and because if the two branches R and C are in parallel, so admittances are added, right, admittances are added. So, the admittance of resistor R, that is your y 1, admittance of resistor R is y 1, that is 1 by R, because opposite of impedance is admittance. And what will be the admittance of capacitor? The impedance is 1 by S C for capacitor. So, admittance will be S C. So, the equivalent admittance will be y 1 plus y 2, that is 1 by R plus S C. So, when you use this 1 by R plus S C, the calculation will be simpler. Otherwise, you can use this R parallel to 1 by S C, then use the formula R 1 R 2 upon R 1 plus R 2. You can do by any method, no issue in that. Now, see, to simplify it, just send this Z P to the denominator side, then what we will get? It will be 1 by Z P, 1 by Z P will be Y P. Now, put the value of Y P, put the value of Z S, we will get the value of L S, that is the loop gain. Now, see, after putting all the values, obviously, since there is a capacitor, so we will get the expression S, S that is equal to j omega. So, just solve it, and after rearranging the terms, we will get this expression L S is equal to 1 plus R 2 by R 1 upon 3 plus S C R plus 1 upon S C R, where S is equal to j omega. Now, put S equal to j omega, let us say it is equation 1, putting S equal to j omega, then in denominator separate the real term and imaginary terms, real part and imaginary part. Now, see, this loop gain L j omega, it is a real quantity, it cannot be imaginary. So, we can put the imaginary part is equal to 0, because loop gain is a real quantity. So, if we put it, then what we will get? Omega C R minus 1 upon omega C R is equal to 0, and this omega is nothing but your frequency of oscillations, frequency of the signal that is generated by this Vin Bridge oscillator. So, we can replace this omega with omega naught. So, what will be the value of omega naught? It will be 1 by R C. This omega naught is 2 pi f naught. So, f naught will be equal to 1 upon 2 pi R C. This 1 upon 2 pi R C is the frequency of the output signal that is generated by the Vin Bridge oscillator. So, we can change the frequency of the output signal just by changing the value of resistor and capacitor R and C in the circuit that I have discussed. By changing the R and C in this circuit, we can change the frequency of oscillation, right. Now, next point is, what is the condition to obtain sustained oscillations at this particular frequency, that is f naught. What is sustained oscillations? I had discussed in the last class. Sustained oscillation means we will get the oscillations of constant amplitude that we want, right. So, for sustained oscillation, the condition is mod A beta, that is your loop gain that you have calculated for Vin Bridge oscillator, it should be 1, right, it should be 1. Now, see this expression and just refer this equation 2, refer this equation 2. In equation 2, in denominator imaginary part will be 0, because the loop gain is the real quantity, fine. If the imaginary part is 0, then what we will get actually? We will get L j omega is equal to 1 plus R 2 by R 1 upon 3, if the imaginary part is 0, right. So, you can see that in which case this loop gain will be 1, in which case this loop gain will be 1, only when your R 2 by R 1 is 2, then 2 plus 1 is equal to 3, 3 upon 3, that is equal to 1. That is why for Vin Bridge oscillator, for sustained oscillations, the R 2 upon R 1 should be equal to 1. It means that if we have selected R 1 is equal to 5 kilo ohm, then what should be the value of R 2? The R 2 should be 10 kilo ohm. These values of resistors are very important to get the sustained oscillation, but in the last class I had discussed one important point. Since the oscillations are generated with the help of that small noise voltage present in the circuit. That voltage is very small, that noise voltage is very small. So, we need to amplify that small noise voltage, and for that initially we set mod A beta greater than 1 for growing oscillations, because initially the amplitude is very small. We need to increase this amplitude, for that we have to set mod A beta greater than 1. But if the mod A beta greater than 1 happens for all time, then we will get the growing oscillations, your oscillations will keep growing. We do not want that. For that what we do? We use the limiter circuit in Vin Bridge oscillator also. That limiter circuit, the function of that limiter circuit is that initially your mod A beta greater than 1, your amplitude will starts increasing, and when it reaches to the desired amplitude, for example, this is the desired amplitude, then the limiter circuit will play its role. It will limit the amplitude. Once the amplitude is limited, for that your mod A beta obviously it will become equal to 1, and for growing amplitude mod A beta will be greater than 1. So, both are important. Initially mod A beta greater than 1 is set, and after that the circuit adjusts itself to get the mod A beta equal to 1 for sustained oscillations. That is why this second point is very important. To ensure that oscillations will start R2 by R1, it should not be exactly equal to 2, it should be greater than 2. 2 plus delta, delta is very small, delta is small, right. So, by doing this, if R2 by R1 is equal to 2 plus delta, if we are taking it, it means that initially we are taking mod A beta greater than 1. If we are taking R2 by R1 equal to 2, it means that mod A beta we are taking equal to 1. So, initially we will take mod A beta greater than 1, it means that if we are selecting R1 is equal to 5 kilo ohm, then R2 should be it should be slightly greater than 10 kilo ohm. Although for mod A beta equal to 1, R2 should be 10 kilo ohm, but it should be slightly greater than 10 kilo ohm for in practical work, right. So, this is important. So, do not be confused these with these two equations. R2 by R1 equal to 2 to get the sustained oscillation, R2 by R1 equal to 2 plus delta to start the oscillation. So, it is important to start the oscillations. We will get the sustained oscillation only when we start the oscillations. So, to start the oscillations it is important, the second equation is important, and after that obviously we need sustained oscillation, we design an oscillator for sustained oscillations. For that the circuit need to be adjusted to mod A beta equal to 1 with the help of mod A beta equal to 1 with the help of limiter circuit, fine. So, this is all about Vin Bridge oscillator. Next is RC phase shift oscillator. So, in RC phase shift oscillators, here we are using inverting amplifier. Inverting amplifier means it will give us a phase shift of 180 degree. It means that the feedback network should provide another 180 degree. To get another 180 degree, what we do? We use 3 RC sections. This one is the first RC section, this one is the second RC section, and this one is the third RC section, and the values of these RC are very important. The values of R and C should be selected such that one RC section should provide 60 degree phase shift, another RC section should provide 60 degree phase shift, third RC section should provide 60 degree phase shift. So, 60 plus 60 plus 60, that is 180 degree. It means that in RC phase shift oscillator we are using inverting amplifier, means 180 degree phase shift we are getting from this inverting amplifier, another 180 degree we are getting with the help of 3 RC sections. Now, we need to calculate the frequency of oscillation for this RC phase shift oscillators. Now, see to it how we calculate it. The feedback network is, I am drawing the feedback network separately just for calculation purpose, just see to it. This one is your C R R R. Now, this is the feedback network. and the input of the feedback is V naught, that is coming from the output, and output of the feedback network is Vf. So, these things I have explained in last 3-4 classes in negative feedback, in positive feedback systems, right. So, this is your feedback network, which consists of 3 RC sections. Obviously, the input of the feedback network is that coming from the output, that is V naught, and the output is Vf. Now, what will be the beta? Beta is important. Beta is the feedback factor. Beta will be Vf upon V naught. So, it means that with the help of this circuit, the lower one, from this circuit we need to calculate Vf upon V naught. It means it is a network problem. To calculate Vf upon V naught, what we can do? There are 3 loops. Suppose that in the first loop current I1 is flowing, in the second loop current I2 is flowing, in the third loop current I3 is flowing, right. Just apply the KVL in these three rules, in these 3 loops, and use the Cramer's rule, and after doing this calculate Vf upon V naught, right. So, after doing calculations, right, we will get the value of Vf upon V naught, that is 1 upon 1 minus 5 alpha square plus j alpha into 6 minus alpha square. What is alpha? Alpha is 1 upon omega RC. Obviously, we will get it because there is a capacitor. Capacitor means 1 by SC. Capacitor impedance is 1 by SC, S is equal to j omega. Then of course, in the equation omega term will come. Separate the real part and imaginary part, and just wherever you get 1 upon omega RC, just replace that with alpha. After doing this, you will get this equation A. Now, from this equation A, again this beta is a real quantity, it cannot be imaginary. So, we can put imaginary part is equal to 0. So, it means that alpha into 6 minus alpha square will be 0. Now, there are 2 terms, either alpha will be 0 or 6 minus alpha square will be 0, but of course, alpha cannot be 0, 6 minus alpha square it can be 0. So, from here what will be the value of alpha? Alpha square will be 6, alpha will be under root 6, although it is plus minus under root 6, but there is no meaning of minus sign because alpha is 1 upon omega RC, frequency is positive, R and C cannot be negative, right. So, there is no meaning of minus under root 6. So, alpha is equal to under root 6. Now, what is the value of beta? Just find it from equation A. Now, this imaginary part, it is 0, just put alpha equal to under root 6, that means alpha square will be 6. So, what we will get? We will get 1 upon 1 minus 5 into 6, it will be 1 minus 30, that is minus 1 upon 29. So, beta is equal to minus 1 upon 29, and for sustained oscillation and to start the oscillation, the condition is mod A beta should be greater than or equal to 1. Initially, we take mod A beta greater than 1 to start the oscillations. After that, to get the sustained oscillation, the circuit adjusts itself to mod A beta equal to 1 with the help of additional circuit, that is your limiter circuit, fine. So, what will be the value of mod A? What should be the value of mod A? Mod A will be greater than or equal to 29, because there is a mod. So, negative sign will be eliminated. So, put the value of beta here. So, we will get mod A greater than or equal to 29. So, these are 2 important results. Your beta is equal to minus 1 upon 29, feedback ratio is negative, that indicates 180 degree phase shift, and mod A is greater than or equal to 29, right. So, these conditions are important because keeping in mind these conditions we design the circuit, fine. Now, what is the frequency of oscillations for this phase shift oscillator? Since we have got alpha is equal to 1 upon omega RC, and what is alpha? Alpha is under root 6. So, what is omega? Omega is 1 upon RC under root 6, omega is equal to 2 pi f. So, f is equal to 1 upon 2 pi RC under root 6. So, sometimes we write it omega naught f naught. So, it means that the frequency of the output signal generated by the RC phase shift oscillator is 1 upon 2 pi RC under root 6. In Vin Bridge oscillator, what we had got? It was 1 upon 2 pi R C. In phase shift, it is 1 upon 2 pi R C under root 6. And also for Vin Bridge oscillator and phase shift oscillators, we have also calculated the condition to start the oscillations and we have calculated the condition for sustained oscillations. So, both the things we have calculated, because that is very important, the condition to start the oscillation to the condition to for sustained oscillations, right. And once we design the oscillator as per those conditions, after that we get a signal of a particular frequency. Now, we want to change the frequency. So, just change the value of resistor and capacitor, and accordingly we can change the frequency of the output signal, fine. So, in this class I have discussed Vin Bridge oscillator and phase shift oscillator. Both are RC type of oscillators and both are used at audio frequency at low frequency. For high frequency we will use LC oscillator, that is Colpite and Hartley oscillators, right. This is the reference. Thank you.